Magnets. They're like magic. You put them into contact with something every day and normal, like this pen. They don't do much. It's pretty disappointing, right? On the contrary.
When you put them in contact with something ferromagnetic, for example, iron filings or another magnet, they attract or repel, but we'll get into that later on in the video.
The most popular legend accounting for the discovery of magnets is that of an elderly shepherd named Magnus. Legend has it that Magnus was herding his sheep in an area of northern Greece called Magnesia about 4,000 years ago. Suddenly his walking stick became stuck to a large black rock on which he was standing on. To the source of attraction, he dug up the rocks in his shoes to find lodestones. Lodestones contain magnetite, a natural magnetic material Fe3O4. This type of rock was subsequently named magnetite after either Magnesia or Magnus himself.
There are 3 types of fields that we will be discussing today. The first one looks like a bunch of vectors being attracted to a single entity. Next, we have a proton and an electron with field lines surrounding them. And lastly, we have a bar magnet with its north and south poles producing field lines as well. The first field is for gravity. Next, we have an electric field. And the third one is a magnetic field, which will be the focus of our video today. Pulling up a table of field equations, as you can see, the equations for gravity and electric fields have been inserted prior to this. The magnetic field equation is equal to the charge Q multiplied by the velocity of charge V and again with B, which is the strength of the magnetic field multiplied by sine theta. And this is the angle between the velocity and the strength of the magnetic field. In general, we could say that magnetic fields are basically electric fields with moving charged particles. Now, let's discuss the principle of electromagnetism. The principle of electromagnetism states that a moving electric charge produces a magnetic field.
Here's an example. Let's have an electron moving away with a velocity of 54 meters per second, perpendicular to a magnetic field with a strength of 1 Tesla. We can actually use the right-hand rule of magnetism to determine the direction of the magnetic field's force acting on the particle. By pointing our forefingers in the direction of the magnetic field, our thumb in the direction of the charged particle's movement, and our palm will face the direction of the magnetic force, and plug in the equation of QVB sine theta, where theta is the angle between the particle and the field, and as theta decreases, the strength of the force of the magnetic field acting on the particle also decreases.
About a year and a half.
Are you glad to be back?
Oh, I'm thrilled. I'm really very, very...
bad?
Oh, I'm thrilled. I'm really very, very happy. I always love being here.
There are two types of magnets that we know of. The first being a natural magnet with north and south poles, and the second being an electromagnet which requires a power source, usually batteries, and it is controlled by a switch which turns the magnet on and off. When another magnet is placed near the natural magnet, its unlike poles attract each other. This means that north attracts south and south attracts north. When the same magnet is placed near the electromagnet, however, nothing happens. Once the switch is closed and the connection in the circuit is made, the electromagnet produces its own magnetic field and is able to attract the other magnet. To calculate the force of the magnetic field, we simply use the equation that we have established earlier, which is QVB sine theta. Taking the values 1.6, 10 to the power of negative 14, 54, and sine 128, and multiplying them all together, we get the answer 6.81 times 10 to the power of negative 18 newtons.
On most modern trains, the wheels are moved by electric motors. The electricity comes from either overhead cables or, in the case of the LRT, an electrified third rail. In the case of high-speed trains, they're powered by electric current collected from an overhead cable by a pantograph. The transformer converts the very high voltage electricity in the overhead cable to the lower voltage needed by the motors in the power car. This tends to be very noisy and expensive, hence why it's not really used by high-speed trains nowadays. Maglev is short for magnetic levitation, in which trains float on a guideway using the principle of magnetic repulsion. Each magnet has two poles, and the repulsive property of magnets is used in maglev trains. However, instead of using permanent magnets, the principle of electromagnetism is used to create strong and large temporary magnets. When an electric field is passed through a wire, a magnetic field is generated around the coil according to Faraday's laws. Magnetized coils run along the track called the guideway. These repel the large magnets on the train's undercarriage, allowing the train to levitate above the guideway. Once the train is levitated, power is supplied to the coils within the guideway walls to create a unique system of magnetic fields that pull and push the train along the guideway. The electric current supplied to the coils in the guideway walls is constantly alternating to change the polarity of the magnetized coils, and this change in polarity causes the magnetic field in front of the train to pull the vehicle forward, while the magnetic field behind the train adds more forward thrust. Maglev trains float on a cushion of air, eliminating friction, and this lack of friction and the train's aerodynamic designs allow these trains to reach unprecedented ground transportation speeds of more than 310 miles per hour. Developers say that maglev trains will eventually link cities that are up to 1,000 miles apart, and at 130 miles per hour, you could travel from Paris to Rome in just over 2 hours. Moving on to the more astronomical side of things, we also have neutron stars, and they are the result of a stellar collapse, usually of a star between 10 to the 29 solar masses. And neutron stars are currently the smallest and densest form of stars that are known to occur in the universe. Unlike most types of matter found throughout the universe, which consists of electrons and neutrons separated by relatively large amounts of space, neutron stars are made of tightly packed neutrons, which are uncharged particles. Neutron stars have extremely strong magnetic fields, ranging from at least 10 to the 4 to 10 to the 11 Tesla, In comparison, the magnitude of Earth's magnetic at its surface is at 0.25 times 10 to the negative 4 or 0.65 times 10 to the negative 4 Tesla, multiple orders of magnitude lesser than that of an average neutron star. The cause of the strong magnetic field of neutron stars are currently unclear. As of yet, current hypotheses include that of flux freezing, that is, the conservation of initial magnetic flux that occurs during the formation of the neutron star.